Okay, the next talk will be given by Professor Kim by excitonic insulators.
Yeah, there is also an overlap in term, with the previous talk, but it's a much more trivial version. It's actually a completely trivial version compared to the compared to the last version. Okay, but before I begin, I would like to thank the organizer, especially Fan, for inviting me here to give a talk. It's my honor. And today I'm just representing me and G talking about electrical transport in an excitonic insulator. And actually, a lot of our works in our career, maybe almost all, were inspired by Allan's papers, many of Allan's papers. But this one is actually special. It's not only inspired by Allan's paper, but also by his patent. Actually, many of you don't know that he has a patent, and actually not just his, but also a Manitoto's patent on about excitonic insulator. Here are some images of from that patent. Allan, if you remember, this is the setting of the experiment that actually you will see again. This is like an electron layer, whole layer separated by an insulator. Then you put some top gates, back gates, and you have a device like this. And this is actually the famous result from Jim Eisenstein's on this differential conductance as a function of the bias voltage that you apply between these two layers. And the idea of this pattern is actually that if you get a negative differential resistance and also a superfluid phase, that actually can lead to very energy efficient logic gates, which is illustrated here, which I actually don't really understand about this diagram. But this talk is actually just about a zero field and high temperature version of this thing here, of this famous work here. Okay. And before I begin, I would like to acknowledge the people involved in this work. Our graduate student, Fang Yuan and Raghav Chaturvedi, and also a former postdoc, Li Guoma, who are really actually doing this work. And also we collaborate with Allan a lot, in particular his student Bozo. I'm not sure whether he's in this picture here, and also Yongxin Zhang, this work. And B and Crystals are from the famous Japanese group. And in the old days, actually, people would like to say that how to really evaluate the importance of theorist work is how much helium you actually use in your lab. In the modern days, we have compressors. We don't really use liquid helium anymore, but not really like burning the liquid helium. A measure for that actually, especially in the 2D materials communities, how much Scotch tape you use, to verify a theorist proposal. And these students and postdocs can verify how much Scotch tape they actually use in doing this work. Okay. So very quick introduction for excitonic insulator. Imagine that you have a semiconductor. You can continuously tune its band gap here. And this is the axis of the band gap. If you actually can tune the band gap to be smaller than the exciton binding energy, the binding energy for an electron and hole, then spontaneously exciton can form in this small gap semiconductor or small band overlap semi-metal. Okay. Compared to a band insulator, it's non-trivial in the sense that it's an insulator, but it actually carries a fluid of mobile excitons, and maybe the ground state is also a superfluid. Okay, and these are actually very old ideas proposed by these giants in condensed matter physics. And in this talk, I'll be talking about a special case. A particular case of this is, we call it a dipolar excitonic insulator because the electron and holes, they live in different layers and they carry a permanent dipole. And so the setting of our experiment is the following, that we have one layer of transistor metal dichocarbonate semiconductor, MOSE2, for instance, another layer of tungsten selenide. And it has a type 2 band alignment before you apply any voltage to the system, in the sense that the conduction band minimum is in one layer, the valence band maximum is in the other layer. And once you apply a bias voltage, VB, then you separate the electron and the hole Fermi level, and by the amount of equal to EB. And as a result, the effective charge gap is reduced from its zero bias gap, which is EG here, by an amount of VB. So it's a EG minus VB. That is the effective charge gap. So just go back to the previous slide. If now you can actually continuously tune this effective charge gap to be smaller than the exciton binding energy, or you actually continuously tune this VB to be larger than the exciton energy, then you can spontaneously populate electron and holes in the system. Okay, and it turns out that this VB here is equal to the separation between the electron and hole Fermi energy. So it's actually equal to the exciton chemical potential. So in this setting, you actually have a continuous knob to tune the exciton chemical potential and exciton density. And furthermore, you can put down the gates, top gate and bottom gate. And you can think of it that the gate here can further tune the electron and hole imbalance in the system. So you actually can introduce extra electrons and extra holes to the excitonic insulator. In some sense, you can just think of it as a doped excitonic insulator. Okay, so compared to bulk excitonic insulators, the electron and holes here are separated in real space. Actually, the separation in momentum space is less significant unless you're doing tunneling experiments. There's no CDW or lattice instability, and superfluid is expected here. And one of the nice things is actually that you can put electron contact and hole contact separately to the layers, so you can continuously tune the exciton density and chemical potential, and you can actually directly establish transport and thermodynamic evidence for excitonic insulators. All right, so how big is the exciton binding energy in the system that I told you about? If you just talk about that you optically excite an electron and hole pair in the system, then they actually are Coulomb bound by the, they are Coulomb bound, which actually is screened by the effective dielectric constant of the environment. And the binding energy of this type of exciton living inside the layer is actually very well measured and theoretically studied. It's about half an EV. Compared to the band gap of the system, it's about 2 EV. So it's about 20 to 30% of the band gap. So it's actually a very large binding energy for something like this. So that would actually have pretty significant implication for the superfluid phase transition temperature for the excitons, for instance. So in 2D, to maximize the degeneracy temperature, you would like to maximize the density of excitons that you can put into the system. Okay, but the excitons are composite bosons. They're actually made of electron and holes. So you can't really put them too close to each other, because otherwise they start seeing the internal structure of the electron hole pair. So how close you can actually pack these excitons before they ionize is that this maximum density is proportional to a factor divided by the ball radius square of the exciton. And this factor here is nothing else but just the binding energy of the exciton. So there are some quantum Monte Carlo studies talking about how big this factor should be. Is actually about 1/2. So if you plug into the number, you have about 0.4 EV binding energy. Then the degeneracy temperature, the maximum degeneracy temperature can be just easily above 1,000 Kelvin. So there's some hope to actually get a high temperature exciton condensate or exciton superfluid in this system. Okay, but that's too good to be true. The reason is actually that that's intralayer excitons. They are very short-lived. You optically excite them, and they have strongly coupled to the photons. Their lifetime is typically a picosecond. So there's not enough time for the excitons to thermalize. And a better approach, a way more realistic approach, is to actually separate the electron and hole pairs into different layers and by some distance. And that would actually significantly reduce the binding energy to about tens of milli-electron volt. And that's still pretty significant binding energy, although it's about an order of magnitude smaller than binding energy there. You can still get pretty decent degeneracy temperature. And actually, that's one of the phase diagrams that earlier proposed in 2014 by Michel Faulkner. And Allan has a similar paper talking about how big the BKT transition temperature could be and the degeneracy temperature could be. Degeneracy temperature is still easily above 100 K before ionization. For interlayer distance of 2 nanometer, you can actually further shrink this interlayer distance. This temperature scale will further go up because the binding energy will go up. Okay, and all right. So this, well, actually, before getting into my talk, I would like to also compare with the famous quantum Hall exciton condensate realized in coupled quantum wells. Jim Eisenstein talked about yesterday, and also in graphene Landau levels. This actually, the exciton condensate that I talk about here is a zero magnetic field version of that, so we don't need to worry about chiral edge states. It has larger exciton binding energy compared to the two systems there. And if I have time, I'll also convince you that a tryon fluid is actually possible in this exciton condensate, really made of electrons and holes. All right, so this is the outline of my talk. I will first talk about perfect Coulomb drag in an excitonic insulator. Then I will talk about emergence of an equilibrium tryon fluid, and if I have a little bit of time, I'll talk about the evidence of finite angular momentum excitons when you put under a magnetic field. All right, so a few more words about the device, how we actually can make this device work. Is actually that we divide the device into two channels. One is the exciton channel here. The electron and hole layers are separated by a very thin boron nitride layer. So the separation in this channel region is about 2 nanometer. And then we also separate the device into another region called a contact region, that the boron nitride here is much thicker, so that with the top gate and bottom gate, we can apply a vertical electric field, and we fix this electric field such that it dopes heavily holes in the hole layer here, and heavily doped with electrons in the electron layer here in this contact region. So that would actually reduce the exciton contact resistance when you go from, when you want to inject excitons into this exciton channel here. So that's the main idea. And in this setting, you can create equilibrium exciton fluid with negligible interlayer tunneling. Okay, so you can actually simulate the electrostatic phase diagram with this setup. And this is the electrostatic phase diagram labeled by PIIIIN. I'm going to explain. And this is actually the band edge of the hole layer. This is the band edge of the electron layer. The hole layer stays straight here because the hole layer is ground. We only apply the voltage to the electron layer. Okay. So these 4 different regions, what are they? The II region just says that, you know, both the electron and hole chemical potential is inside the gap. Both are in the intrinsic region. So this is pretty boring region. And IN means that, you know, only the N layer is doped with the electron. PI means that only the P layer is doped with holes. And the interesting part is this PN region here. The electron layer is doped with electrons and the hole layer is doped with holes simultaneously in this region here. Okay. And we can actually measure this phase diagram using using capacitance measurement. Jim actually talked about yesterday. The idea is that we apply a small AC excitation voltage to the top gate and measure displacement current through the bottom gate. If this bilayer system is compressible, it's going to screen out this field. And if actually it's incompressible, the penetration field can just go through and you can detect a signal. 1 over this penetration capacitance in the simple limit is proportional to the charge compressibility of the entire double layer. Okay. And this is the experimental result. The CP, penetration capacitance, normalized by the gate-to-gate geometric capacitance as a function of the gate voltage under 0 bias. So we only have a shared electron and hole Fermi level. And the VG here just tunes the Fermi level up and down. So when the VG tunes the Fermi level to hit the conduction band minimum, and you get a sharp drop in the penetration capacitance signal here, that's the Morley band edge. On the other hand, when you hit the valence band maximum, that's the tungsten band edge, valence band edge here. So you can directly read off the gap size of this, basically read off this gap size here by just the distance between these 2 sharp edges, and it's about 0.52 EV in this setting here. You can also apply a bias voltage here, then effectively you reduce the charge gap from EG to EG minus VB here. And this is actually the plot of the penetration capacitance as a function of VB and VG. VG moves the average of the electron hole Fermi level. VB tunes the separation between the electron and hole Fermi level here. And you can directly read off the gap size with this, the distance of this arrow here. And with the increasing VB, you can actually see that the effective charge gap size will go to 0 at some point here, and the system becomes compressible. Okay, red means incompressible, blue means compressible. All right, then you can compare to the calculated electrostatic phase diagram. It agrees pretty well. This is an incompressible region, which is the II region here. Then we have the IN, PI, and also this PM region here. Looks pretty good overall. But if you look a little closer, you can actually see there is a line here that is actually the electron and hole, the PN threshold. Actually, it's pulled down from this tipping point here by about 30 milli electron volt here. So that actually suggests that there is an incompressible state here that carries electron hole pairs already in the system, because we are already in the PN region, but the state is actually incompressible in this region. So to really show that there are indeed electron holes here, there's nothing better to directly drive an exciton current in the system, that you can directly see an exciton current inside this region here. All right, so that's what we do here. We do a drag counterflow experiment. We drive a current in the electron layer and measure the current in the hole layer. And if you have bound electron hole pairs, you basically have perfect Coulomb drag. The drive and drag current, the magnitude should be equal to each other. And if you just have an electron hole plasma and you have a small frictional drag, basically it will be zero in the zero temperature limit. Okay, so this is the result. This is again the phase diagram measured by penetration capacitance, II, NPI, and PN region here. And this is basically the map for the drive current, which is the electron layer here. And red means that you have a drive current. This part you have no drive current, which is totally expected. You only have a drive current when the N layer is turned on, so only in the IN and PN region. So you have a drive current only inside this region here. And the interesting thing is actually where you actually can find the drag current. And it turns out that you can only find the drag current here inside this hotspot with the triangular region that you have overlapping with the PN region here. So you get only the large Coulomb drag here in this region. Okay, so that's expected where you actually can find excitons in this incompressible region, but you do have an exciton fluid there. And let's examine a little more closely. Just draw a line like this diagonal line here, which actually the electron and the hole density is exactly equal to each other, n equal to p along this line here. And just make a line plot. This is a current versus the pair density or the bias voltage along that line here, okay? The black curve is actually the drive current. So it turns on when you start doping electrons into the electron layer, and then it stays on after that. The red is the drag current. It actually becomes the same as the drive current over this region, which is an excitonic insulator. But once you go beyond the excitonic insulator, actually the drag ratio actually drops very quickly from 1 to 0. And this, we think it's a mod transition. Well, Shankar has 6 papers talking about that this is not a mod transition, but it should be a crossover. And in the next few slides, I'm going to try to explain to you, well, or try to convince you that whether this actually could be a mod transition. All right, so, and also I would like to highlight that the tunneling current is really negligible in this region here. This is multiplied by a factor of 100, and that the tunneling current is actually very small compared to the in-plane current. So we don't really need to worry about the tunneling current. Okay, so if you're still not convinced this is another device, basically the red is the drive current, the black is the drag current. And here we drive the whole layer and measure the drag in the electron layer. And you have something like this, you still get a perfect Coulomb drag in the excitonic insulator region. Then we switch around, we drive the electron layer and measure the whole current, which is on the right-hand side here. And you actually get the same perfect Coulomb drag in the same excitonic insulator region. And furthermore, you also have the same exciton current in the system. So there's total reciprocity in the system. No matter which layer you drive or drag, the result is actually the same inside this excitonic insulator region. Another interesting thing you can actually do is to just do an open circuit measurement. You do an open circuit in the whole layer. And in that case, because of the bound excitons, you are not really able to drive a current in the electron layer in the excitonic insulator phase, because the whole current is not allowed to flow in this open circuit setting. So in this setting here, we just bias a voltage in the electron layer by 1 millivolt AC bias. And what we measure, interestingly, is actually that in this excitonic insulator region, the whole layer voltage is also almost the same as 1 milli-electron volt. So the 2 layers really behave like they are totally locked as a single layer whenever you hit this excitonic insulator region, and outside it just quickly drops to 0 when the 2 layers become decoupled from each other. Okay, what's the temperature scale of this excitonic insulator? As long as you stay in the excitonic insulator region in these 3 curves here, in the low pair density, you get perfect Coulomb drag up to about 20 K for interlayer separation, about 2 nanometer boron nitride. We expect that if you reduce this boron nitride thickness, you can further increase the binding energy and push the energy scale up. And once you go beyond the pair density, that actually the electron hole pairs ionized into an electron hole plasma, you actually get a frictional drag, which will go down to 0 in the 0 temperature limit here. Okay. So this is actually now the modified phase diagram of the entire system. Instead of just having a PN boundary just exactly overlapping with this tipping point here, actually the PN boundary is actually pulled down by the electron hole interaction. And there is a triangular region here that you have an incompressible state, but carry a mobile electron hole pairs in the system that you can drive an exciton current. And the amount that it gets pulled down is actually equal to the exciton binding energy. In this case, is 30 milli-electron volt. Okay, so these two slides, I'm going to just try to address Shankar's question, whether there is a Mott transition or no Mott transition. This is actually a drag resistance measurement. The whole layer is open circuit. We only try to drive a current in the electron layer. And if it's in the exciton insulator region with a low pair density, this becomes an insulator. So this is the drag resistance versus temperature. It becomes an insulator at low temperature because the holes are not allowed to flow. So it becomes an insulator. And once you cross some critical density, we call it the Mott density, and you actually can see that the systems can suddenly become like a metal with actually the drag resistance in this case scales with a t-square with a coefficient A here. So this really looks like there is a Mott transition from excitonic insulator to an electron hole plasma. But the really important thing is actually that we try to analyze how this A coefficient here scales with the pair density. And this is a plot of the A coefficient here in ohm per Kelvin squared, scales with the pair density in the system that you can continuously tune. And it turns out that it actually diverges by 3 orders of magnitude, following a phenomenological power law that is 1 over MP minus the pair density minus the Mott density, okay? And there are frictional theory. Actually, Shankar, you have a theory, and Allan also has the theory saying that the A coefficient should scale as 1 over the MP to the cube power. The pair density, in that case, actually, it would diverge to 0 here. So it seems that this experiment really suggests that there may be a quantum criticality around this Mott density here, and there's something that gets reset in this power law dependence that we should not measure the pair density from 0, but instead we should measure the pair density from the Mott density here. And although this is like a finite temperature experiment, we try to extract this parameter and tell something about whether there is a 0 temperature quantum critical point. So maybe there's an evidence of exciton Mott transition, or maybe a continuous Mott transition at the Mott density. Okay, finally, I just want to quickly talk about another measurement scheme that you can do in this kind of setting. Here, we actually can just put the electron layer in an open circuit. No electron is allowed to flow. And we just measure the 4-terminal resistance in the tungsten layer. And because of the Coulomb interaction between the electron and hole layer, you just measure the resistance, the 4-terminal resistance in one of the layer, it actually tells you a lot about the interlayer Coulomb interaction. Okay. In particular, if you're bound electron hole pairs, you should have a diverging resistance at low temperature. So this is a map, again, of the 4-terminal resistance of the tungsten layer versus VB and VG here. This is the excitonic insulator region. We have a diverging resistance in this excitonic insulator region. But you can also figure out that there is actually an interesting region here. There's this line here that if you do a temperature dependence, for instance, cutting along this line here, you get exactly at this point that it becomes a diverging resistance with decreasing temperature. And the interesting thing is actually that this line here happens exactly at the P equal to 2n line in the phase diagram, when the hole density is about twice of the electron density, okay? And what's happening here is actually that when you just tune exactly at this condition here, the hole density is twice the electron density, good, that you actually form a trion pair, trion bound state in the system here. And because the electron is not allowed to flow in this layer, then you get an insulator when you just measure the hole resistance in the layer. So that's an indication or evidence forming an equilibrium trion fluid when you tune the density to be just exactly right. Okay, this is the final technical slide. And so far, everything I've been telling you is under 0 magnetic field. You can also turn on the magnetic field in this electron hole layer system. And you still get this perfect Coulomb drag in this triangular region that has an exciton insulator. And in this case, it's actually 0 angular momentum excitons. But you also actually can get substantial Coulomb drag up to about 0.5 when you tune away from charge neutrality, when you start doping the excitonic insulator by electron and holes. The interesting thing is actually that when the Landau level index is of the electron and hole, the difference is equal to an integer, you actually get substantial Coulomb drag also in this region here. And that shows indication the system may have a tendency to form finite angular momentum excitons in the system that, the Landau level index is different by integer values. All right, so this is summary. And I hope that convinced you that there's a, equilibrium exciton fluid and also a tryon fluid. And maybe there are indications of a finite angular momentum excitons. And there are lots of things that one can still do. But the most important slide, congratulations, Allan, on your amazing contributions. The conclusion is that we're trying, not quite there yet, and more works need to be done, especially in terms of whether the excitons really carry is a superfluid space or not, whether the exciton resistance is 0 or not in that phase. I think one should really try harder to measure it. And with this, thank you for your attention.
Thank you very much. We have time for 1 or 2 questions.
All right, so thank you very much. Just a clarification first. So these excitons you've been talking about, they repel each other. Is that true?
They repel each other.
Right, so that's why you don't worry about biexcitons entering the system before.
They actually carry the
right.
dipole.
Yeah, because they're dipoles, right?
Yes.
Exactly, right.
Yeah.
So could you sort of summarize which of these observations you think is the strongest indication that you do have coherence between these excitons, rather than you just, liquid helium can be normal or superfluid, right? So how do you know that you do not have just a, normal liquid helium in quotation marks of excitons here?
Well, I would say that, none of the experiments so far show that with 100% confidence that this is really
right. Yeah. That's the impression. So,
but I think there are multiple experiments that show that when you hit this excitonic insulator region, the 2 layers really strongly coupled, that they behave like a single layer system, right? They have a perfect Coulomb drag, and you also bias a certain voltage in the drive layer. You also can measure the same voltage in the drag layer.
Right.
It just really shows that the 2, they behave like a single layer system, but there is no experiment so far that shows that it's really like in a phase coherent state.
But can you see some sort of dramatic drop in counterflow setup, right? Can you see that there is all of a sudden a drop in dissipation in counterflow, and say that maybe they do not?
So then we need to do a 4 exciton terminal transport measurement that we are not able to do yet, because we actually only have two contacts on the electron 2. Actually, we have multiple contacts on the holes, but we only have 2 contacts on the electron, so we actually can do only a 2-terminal exciton resistance measurement. So if we have 2 more of this pair of contacts in the system, then we can also really perform like a 4-terminal exciton resistance measurement. Then that will, as you said, you would have a job below the PKT transition temperature, for instance.
All right, thank you.
Perhaps 1 short question before we move to Anton's talk.
I can follow up that questions. I think it was a beautiful data, but I thought kind of you showed the 4-terminal data. So I thought you are now ready to measure the counterflow resistance measurement on those kind of the devices.
Yes. No, the only 4-terminal on the whole layer.
Yeah.
We don't have a 4-terminal on the electron layer.
But probably doesn't matter, right? Because you can make the kind of counterflow and measure the 2 terminals, the 4-terminal on the one side. I think that should.
Yeah. I think so the short answer is actually that for some reason we have not performed that experiment, and you're just talking about if you flow an exciton current and just measure the voltage drop in one of the layers only, right? And that we should have an answer soon.
Okay.
Yeah.
Okay, thank you very much. Let's thank the speaker again.